Okay, good afternoon. Welcome to this week's colloquium. So today we are very happy to have our colleague, Professor Xiong Yi, to give a talk. Well, even though he's one of our colleagues, but let me still spend some time to introduce him, mainly for the students who doesn't know much about him. So Professor Xiong was involved in two important discoveries in particle physics. One was the first discovery of the direct CP violation in the neutral kaon system. And actually, that's the first discovery of a direct CP violation in particle physics. And the second one was the measurement of the so-called theta-13, the smallest mixing angle in neutrino oscillation. And that was more recent. Before joining NTU, he was working at Fermilab, one of the spokesperson of the K-TAP experiment. And he came back in the year 2002, and immediately he received the Outstanding Scholar Awards in 2003. And then he served as the department chairman for a few years. And after that, more recently, he received the National Chair Professorship from the Ministry of Education in 2014. And in 2016, because of this theta-13 measurement, he shared a new prize called the Breakthrough Prize in Fundamental Physics. And the same year, he received a NTU professorship from the university. So, as I said, he involved in many important discoveries of particle physics. And in recent years, he's involved in another important experiment called a Koto experiment in Japan. And recently, there's some exciting results. So today we are going to hear him talking about this exciting news. So let's welcome him.
Okay. Yeah, thanks, Stanway's introduction. So today I will try to tell you about, why do we study this very rare KM decays, and also how do we do it, okay? Then of course, I'll show you some latest results. And so everything, of course, when I started working on the KM experiment, actually, after I graduated from Columbia University, actually, in 1986. And that's the first time, actually, I joined the KM experiment, the Fermilab. And basically, the reason, of course, is all start with the KM CP violation, okay? And basically, in 1964, Jim Cronin and Val Fish, they discovered CP violation in the decay of K-long decay. Cation actually, there's a charged cation and also there's neutral cations, so-called K-long and K-short, long-lived one and short-lived one. And the long-lived one, actually, the short-lived one usually decay to 2 pi. Long-lived one usually decay to 3 pi, like this. And they discover actually K-long decay to pi plus pi minus. It's the first time in this PRL paper. And you can see, okay, when you have 3 pions, it's a CP odd final state. And when you have 2 pions, the CP even final state. So later, of course, experiment confirmed, not only decays to a pi plus pi minus, also decays to a pi 0, pi 0. So it's only based on 45 events, okay? And they're 1964 discovered. Actually, the experiment they tried to do has nothing to do with the so-called CP violation at that time. They didn't even know, okay, their CP violation exists. What they want to look for is, they have this so-called neutral beam coming in from the target somewhere. And when you actually produce the neutral cation near target, usually is the short-lived cations, K short, will produce and will basically decay away. And the long-lived cation will basically stay until, okay, go into this collimator and experiment. So what they want to do that time is actually so-called regeneration phenomena. Is if you put, I have to disable. Okay. So basically they try to study something like a regeneration phenomenon. So when you have a K-long usually K-short usually is the it's a K we call K0 and K0 bar, particle superposition. So when they come in and if they interact with some we'll call regenerator like a target, and the K-short will actually regenerate and decay to 2 pi. And during this studies, and I think they only wrote like 2-page proposals, and they actually taking out all the regenerator and try to double check. And so this region actually you can see when the K-long comes in actually decay to 2 particle pi plus pi minus with a 2 charge spectrometer with the magnet, the scintillator, and even the so-called Cherenkov to do the particle identification. And so in this decay region, they put the helium bags. Okay, so they try to reduce, so-called regeneration phenomena. However, if you look at this is in the KLMS. This is below KLMS is above KLMS. They got the peak. This is a cosine theta equal to 1, basically peak forward. Okay, so they found those events. So that's the first so-called discovery. Of course, later on, there are a lot of study on the kaons. We know kaon actually when they produce, and they have a K0 or K0 bar when they actually produce it, say from the target, and it's either the SD bar or S bar D. So the strangeness, you can see, okay, has to be -1 or +1. So the since K0, K0 bar are the the similar, so-called the mass second state. So quantum mechanics can immediately try to mix them. So when they propagate, and actually can mix. So basically, you can see there are two so-called we call CP eigenstate, and if the so-called K long K short are CP eigenstate, the particles in the weak decays, and the K1 is the CP even, K0 plus K0 bar. K2 is the CP odd, is the K0 minus K0 bar. However, we already knew, okay, the 2 pions are CP even state. So 2 pions should favor so-called the K1, right? However, the K long, K short, actually, this is also another quantum mechanics. You don't have to be a perfect mixing, okay? It can, the superposition can choose, in some sense, nature can choose whatever they want. And it just happened, okay? The K short is the short-lived. You can see the so-called the lifetime. This is the speed of light, c times. It's about 2.67 centimeter, okay? When they actually move very slowly. The K long is about 50 meters. So you can see, they can travel actually quite different distance when they decay. And K short is K1 plus a little bit, so-called the we call the round CP state. Then the K1 plus epsilon K2. And K long is K2 plus epsilon K1. So K long is mostly so-called the CP out. So from the decay, it's very clear. K short favors 2 pi. Okay, almost 100%, right? If you add it up. Then with a few other very small branch ratio. But K long mostly is the 3 pi, pi plus pi 0, you can see, and also we call semi-electronic decays. However, it has a very small part, about 0.1 to 0.2% decay to 2 pi. So that's so-called the discovery we call the epsilon. This epsilon, the coefficient. It's about 2.3 times 10 to the minus 3. So CP is violated, but it's not very large amount of violation. So after that, of course, the theories and also experiment has much better understanding, especially the after the Kobayashi Maskawas and introduced so-called the 3x3 matrix element for 3 generations. So we have 3 generations of the the quarks, and you have this complex 3x3 unitarity matrix. So these unitarity matrix usually there's a 6 unitarity angles, and the relationships. That means it can form like a triangle in a complex plane, and the area, the triangle area, actually is proportional to so-called CP violation. So that's how we understand right now. And you can see this JCP usually proportional to some product over here, and proportional to so-called the sine theta Cabrillo angle, cosine theta Cabrillo angle, and times another imaginary part of this relate to the top part, the contribution. So this is the so-called the CK matrix element forms so-called the triangle, and this triangle in the Kaon system typically actually it's quite long. Okay, we just draw it this way, and also for example in the B system, okay, it has not also the similar triangle, but maybe more more uniform. So anyway, in the chaos, with a CK matrix element, usually we can parameterize with the so-called Lincoln-Wolfenstein parameterization, and you can describe so-called like eta and rho. Okay, it's on the complex plane. So in here you actually I draw something like alpha, beta, gamma. These are from the, compared with the so-called B system. But in the chaos system, the height basically is direct proportional to CP violation. And these modes come in like k to 2 pi, epsilon pi of epsilon, and I will describe it later. And k log to pi 0 limit bar, also k log to pi 0 e plus minus, and even pi 0 mu plus mu minus. So these are the pi 0 with, 2 leptons, either charged or the neutrals. And on this part, usually probe so-called rho, and it's like a k log to mu mu, these modes. And then there are also on this side, to fix this again.我没有办法关，你可以把它选一个，对。So the K plus actually is on this side, the contribution. So there's a so-called rate decays. These are all rate decays, okay? And you can see the so-called the imaginary part of the lambda t is proportional to the so-called the some constant a squared lambda 5 and the eta this one, and the real part is proportional to the rho here. All right. So back to the experiment which I was involved in the Fermilab, and that was the first time we tried to measure so-called the direct CP violation. So the direct CP violation, as I said, okay, we have this mixing, and which generates so-called the indirect CP violation through this epsilon. It's about 2.3 times 10⁻³ and however the so-called CPR, if it actually can directly decay to 2 pi, then you have two paths. That means the the amplitude, you have some kind of superposition or interference also. So the question is, how do we measure it? So to really distinguish between so-called the direct CP and indirect CP, and what we do actually forms this so-called the double ratio, okay? And we have to measure so-called k long decay to pi plus pi minus versus divided by k short decay to pi plus pi minus. This is just in terms of rate. And also k long decay to pi 0, and the k short decay to pi 0, pi 0. So the charge kaons, of course, we can use so-called the charge particle spectrometer to measure the momentum and form the invariant mass. But the pi 0 usually decay to 2 photons right away. So there are 4 photons in this final state, and we can only rely on the so-called the photon shower energy measurement. So basically, the epsilon point of epsilon experimentally is try to measure this double ratio compared with the 1. Okay, it's only 1, point something, and then divide by 6, 0.6 subtract by 1. So if this is non-zero, then it's direct CP. Also means the this rate, this transition rate, is not equal. Okay, so the result, of course, after many years, the experiment preparation and also taking data. So you can see the early data from so-called E731 in 1993, and that was negative. So that was not negative. The early one, there's some negative one we didn't include. So this one is almost consistent with 0. Then there are NA31, which is looks like a 23 plus minus 6.5. Then there's improved the CERN experiment NA48, and also the KTEF in the this is a 2007, which will give this kind of number. So you can see that finally these large errors and reduced to a small. Then error bars. And finally, the world average, you can see somewhere around, 16.8 times 10 to the minus 4 with the, small error. Of course, these two numbers not still, error bars touching. So they are not quite, overlapped in error bar. So the confidence level usually at that time we gave about 13%. All right. So this is the story experimentally. So experimentally have seen, okay, direct CP violation through this epsilon point of epsilon measurement. However, theorist, has trouble to really calculate this. Partly because this is a non-perturbative type calculation. It's very hard. And this is from the Andrew Burras, summarize. I think in early September in the KM conference, you can see the basically besides proportional invariant part of this VTD, VTS star, and you see 10 minus 4 over here, and there's several contributions. These contributions all from the so-called penguin diagram. We call the QCD penguin or electroweak penguin, and their parameters usually we call back parameters from the from some of those from those contributions. So those back parameters actually was hard to really calculate reliably. You can see the there various different versions of the estimations. Some of the error bars still large, and even with this, okay, the theory calculation, many different group, and also with different assumptions. Some are lattice calculations, they're all over the place. Okay, you can see, this is a small, like consistent with 0, 10 to the minus 4, and this is be larger, and this is the largest one, 15 times, and 10 to the minus 4, but with large error bar. So theories has a lot, large amount the uncertainties in this calculation, even with the lattice calculation, almost 30 years. Okay, so compared with experiment, this is the current average. We know is already quite precise. So the questions, are those number, consistent with 0 real from the theory calculation? If not, then the if it's real, of course, then it's inconsistent with the experimental results. Then that means there may be some new physics. Otherwise, the theorist has to do a lot of improvement in this calculation. So you can see over the last 20 years, and besides epsilon prime over epsilon, and we're experimentally we want to look for something more firm. So this comes into this so-called the big long marching on this measurement. So K2 pipe linear bar case in the standard model. So I said, okay, in the standard model and in the pi to linear bar, you will have to go through, because it's a neutrino. So you have to go through this so-called electroweak penguin type, and with either top quarks or Z's. Okay, and this is the typical we call box diagrams. And in the pi, usually here you can have either gluons, then make quarks, or the so-called gammas. So it is true. Okay, in the pi case, it's a lot more complicated. There are a lot more diagram you have to handle, and there are interference in there. And especially, I think the Z penguin has opposite sign to the gluon penguin. That's why calculation is very difficult. So with the only this kind, the Z penguin, and theoretically, basically, this is very clean. And a lot of the calculation you can base on the measures, for example, parameterization with the measure the semi-leptonic K3 decays. It can deal with, this is all short distance interactions, and the top quark dominate here, okay? And so it's well controlled. so-called charm contribution. C-quarks contributions, it's not that big. So for example, the Brewers has done the calculation. This is in the 2015, I think, and 3.4, okay, plus minus 0.6 times 10 to the minus 11. However, the branch ratio is tiny, really tiny, okay, 10 to the minus 11. So it's mind-boggling type experiment. So, and in the K long 2 pi nu bar, basically it itself is so-called a flavor changing neutral current. And it actually has those flavor changing neutral current loops, which just here, the Z penguin is a flavor changing neutral current for the S to D couplings, okay? And basically has the highest CKM suppression. And if you base on the calculation, if you compare the charge K plus, you remember charge K on the side, and the K long is the height. So the triangle. So the pi nu bar, and you can see charge K basically proportional to those parameters, and neutral is proportional to those. And you can see they all at around 10 to the minus 10 to 10 to the minus 11 region. So so basically why do we want to study? Because it's clean, but experiment is very hard. So but also we can compare, okay, so-called the charge K-ion, and also the neutral K-ion, and we actually can probe so-called the standard model unitary triangle. We can probe the so-called CP violation, flavor changing neutral current, just see the calculation and the experimental result. They're consistent or not. So today, actually, I want to report both, and both experiments have some new results. So this is the NA62's slide. Basically, you can see the penguin like this. So this is state of art K plus pi plus nu bar experiment before actually announced the new result. The previously at Brookhaven, in the U.S., there are 2 experiments consecutively, with some operate, so-called E787 and E949. You can see the signal is these spots, okay? And they have, basically you can count 1, 2, 3, 4, 5, 6, 7 events. And based on those 7 events, these are the middle part is actually the allowed decay, K long, very huge branch ratio, K long to pi 0, pi plus pi 0. So this decay branch ratio they measured, not very good, the so-called uncertainty here, but about 1.7 times 10 to the minus 10. And the NA64, the first round they also have 1 event, okay, 2016 data, and also they quote some limit over here. So basically we have this relationship between so-called K plus to pi plus nu bar and also K long to pi 0 nu bar, and based on some theoretical argument about the rate of the branch ratio, and you can draw some line called Grossman near bound, and typically allow regions to this part, and you see this is 10 to 11 I modified, okay? So there's a huge region actually at the center models here, okay, just here, and there's a huge region it's not explored, and it's also possible with new physics and contributions in there. Now, if we find out the branch ratio, the so-called branch ratio, is not at the standard model level. All right. So the Koto experiment actually has run since 2013, and the first largest run, the big statistics come from 2015. It took a while to really analyze this and come up with this so-called PT versus Z plot. PT is the transverse moment, and Z is the decay region. Okay, so you can see that this is a signal region, and there's no event, but there's some background here, and it's over here. And this is based on the single event sensitivity, and also we can set the upper limit about 3 times 10 to the minus 9. This is already 10 times improvement in the previous, previous generation experiment at KK. So this is published actually early this year. But in the meantime, actually, we're analyzing the data after 2015 up to 2018. So this is the collaboration in the COTO, and of course, the National Taiwan University is part of the collaborators, and usually, occasionally we have a collaboration meeting, just here. So you can see this is the not very big collaboration. The idea is how to do it. Okay, now how do we do it? So typically we have a proton hitting some metal target, and usually we want some angle because the neutrons, they are neutral particles. They are very stiff. Then with some, the so-called beamline collimators, magnet, and finally the neutral beam can come out this way. It's like a pencil beam, okay? And then this beam, after some distance, so the K short decayed away. All the other, like hyperons, all decayed away. But the K long survives into this decay region. So this decay region, usually we actually is quite large and put in the vacuum. And then we need to have so-called hermetic coverage. That means we try to cover all 4 pi. And in this region, we can detect so-called the 2 gammas. 2 means from the pi zeros. Then the neutrino, of course, they fly away. But then if K long decay to 3 pi's or even 2 pi's, 2 pi zeros, they should be other hits, surrounding the called beetle detectors. So this is idea we call the pencil beam plus hermetic beetle system. The problem on this decay is a neutral decay. When they come in, you don't know. You can't see it, right? When they decay, it's only pi zero. It's also neutral. So sometimes, so we joke, it's the nothing in, nothing out experiment. How do you do it? Okay. So the only thing we see actually just these 2 photons. All right. So the COTO experiment actually located in the J Park, near the so-called the Pacific Ocean, right next to the ocean, and it's north of the Tokyo. I think it's about 3 hours bus drive, and this is on the small village we call the Tokai village. We usually in Chinese we call Donghai. Okay, Donghai Chun. So you can see there's a linear accelerator over here and goes into a 3 GeV, the synchrotron. Then the accelerator to 3 GeV, then send out into this ring. They call the main ring. Main ring can accelerate up to about 30 to 50 GeV, then send to Hadron Hall. Can do experiment here. And there are other, for example, there are material life science experiment with the neutron beam and the muon beam. There's also neutrino beam. Goes to a so-called Kamikanди. They call the Super K experiment. Okay, so it's a multi-purpose, the laboratory. And so this is the COTO beam line in the Hadron Hall. You can see it hits the primary beam, hits the so-called T1 target. It shares the beam with the charged kaon experiment, the nuclear physics. And we're here, this line. Okay, this is so-called K-long beam line, some angle. And over here, of course, the beam power. This you can see. This is in terms of kilowatts. Okay, 40 kilowatts, and it's trying to going into 100 kilowatt at maximum. We're somewhere here. Okay, about 50. So the Colo experiment, the design, you can see we have very good so-called beam design. We call the confirmation system with the sweeping magnet and then with some absorber. Then the K-long comes in. So this is almost like at least 10 meters distance. And then the K-long comes in. This is another almost 10 meters, for decay reading. Okay, so the signal detection, of course, we only see these 2 photons. And that means we have to rely on the so-called reconstructed pi-zero PT, which should be non-zero because the 2 neutrinos fly away. And the versus so-called decay region. This is the decay region. Then you can see the Monte Carlo, for the signals is populated somewhere over here. And the PT usually is about 100, like 120, This is wrong. MeV over square, not GeV. Okay, so you can see the mode. There's a K-long decay to those semi-electronic mode, 3 pi-0 mode, and also K-long decay to 2 pi's, and even the K-long decay of 2 photon. Okay, it's 10⁻⁴. So these are all the so-called known decay modes. So the detector, you can see at the end to detect the photons. This is what we call CC-MADA crystal detectors, and the CC-MADA, these are all sitting in the vacuum vessel. Okay, and these has small crystals and the large crystal. Small one is about 2.5 centimeter by 2.5 centimeter and 50 centimeter long. The large one is 5 by 5 centimeter and 50 centimeter long crystals. This is the best, so-called EM calorimeter in the world. Okay, the best, the energy resolution, also position. I cannot say position. Best energy resolution. Then in front of it, we have a so-called charge veto planes. These are scintillators to veto the charged particles. And the veto, we call the inefficiency, should be less than 10⁻⁴. Then in front of, you can see the surrounding here. These are, we call the main barrel. Okay, the main barrel vetoes. These are lead scintillator device. They are lead and scintillator sandwich. And those veto actually with the earlier, I think, so-called the beam study we had, we knew how to construct this, how thick the lead layers, how thick is the scintillators to optimize. So we can get the so-called inefficiency below 10⁻⁵. Okay, and in the middle here we have this like a color counter. Okay, and then there's this is front. We call the front barrel insert over here, and this is the back behind the CC-MADA, and there are more beam vetoes in this region. Okay, so this is generally, we use quite a bit veto device to do this experiment. So to take data, and usually we'll have a so-called trigger. Level 1 trigger, for example, we can sum all the CC-MADA energy, and you can see there's some threshold here. And basically, we can also require, at least online, after some threshold, no big energy in the veto counters in those regions. So that we call the CV. There's also no the charged particle going through the CV plane. So this is online. Of course, the online threshold is usually higher. Then we can do the offline studies later. And the other things actually we do is we try to count number of clusters. Since 2 pi-0 has 4 clusters, and pi-0 only has 2 clusters, and 3 pi-0 has 6 clusters. So if we actually can do a quick online, the calculation about the cluster counting, this is a very interesting so-called the algorithm. We actually can do them in parallel in the CC-MADA. Basically, the idea actually is the next page. you can actually go around any clusters. Then you actually make so-called the left turn and right turns. And so you count number of so-called left turn minus number of right turns. It happens to be divided by 4 is equal to number of clusters. So you can see, the single clusters going around 4 times. Like this one, you can always count. Okay, so you know how many number of clusters, and you can do it very quickly in the hardware. So this has been used actually quite a long time ago at Fermilab, then at KTAB. Each time actually we build different hardware processor, and then also the Dakota. But the algorithm basically very similar. So the number of kaons actually usually we reconstruct k down to 2 pi. Even the CP, violate decay mode, but still you can see it. And so the running, basically you can see, we start with the 2013. Actually, we would like to start with 2011, but that time we have there's a big, the earthquake and tsunami in Japan, and we already actually had everything ready. I think in February, and then March 11, and shut us down for almost a year. Then we started in 2013 with a very short run. It actually has another accident in the accelerator, shut down again. Okay, you can see we did not start very smoothly. So in 2015, this is the data I showed before, the results. And then we have actually pretty good running. And but the beam power, actually you can see, the beam power actually was slowly rise, okay, up to about 40 kilowatt. Then 2016 to 18, each year we run about 2 to 3 months, I think, maybe 2 months roughly. And you can see the beam powers almost reach 50 kilowatt. So this is the K down to 2 pi 0 mass peak with the background and Monte Carlo simulation. You can see we understand our city model quite well. So this gives us the so-called the number of K longs at the beam axis about 7.1 times 10 to the 12. And this is almost 1.6 times, more than the 2015 data. And the background, of course, is one of the main problems in this experiment, how to reduce the background. And you can see the data Monte Carlo comparison with the 2 pi's and also with the 3 pi's, and in those plots. So our background actually, quite large backgrounds, especially, we have some kind we call the accidental things. It means that you can have some randoms, things happen in the fake calorimeter, and they may be associated with the beam, maybe not. So these has to be studied. Anyway, so the way we do it is we take some kind data we call from the target monitor, we call accidental data, and those data we actually overlay with the so-called the Monte Carlo. Okay, Monte Carlo on those different decay modes, and we need a very large statistics to get low background. So one thing we try to do is try to do the so-called blind analysis. This is not easy to do. Blind analysis means that we don't look into the signal region at beginning, and we have to base on our study of the background from Monte Carlo, and then decide, okay, what kind of signal box in the so-called blind region. Okay, so what kind of background? I just illustrate. Okay, one thing is like a neutron background. The beam comes in. It's a neutral beam. It contains not only the K long, it also contains neutron. And the neutron actually, the beam usually has some tail. Okay, even the tail probably around below 10 to the minus 4, around 10 to the minus 5. But it's not the best design we have compared with the earlier experiment, because we have to share the target without the beam lines. So those has some so-called we call halo neutrons on the tails. They may hit something, near, the so-called entrance of the detector, then they scatter. And they also may generate, so-called secondary, and can be pi zeros. They even can hit somewhere near the so-called charged pitot and generate so-called the etas. So you can see these are the typical, so-called the Monte Carlo simulation of those events. And of course, when we reconstruct, they tend to, smear out and shift into our decay region. Okay, if you're not careful. So, for example, this is one of the study for the neutron background. And neutron background, actually, we compare with so-called physics data, and also we have this very special run. We put aluminum target right in front of the entrance. And once you put it in, okay, it's not very thick. It's like a few millimeter. Then the neutron, the beam can interact. Of course, you can have pi zeros, you can have charge pi, you can have neutrons, and then they spread over here. So we can compare so-called distributions. And we try to do a blind analysis. That means this region generally is just black out. Then we compare it outside. You can compare the shapes, those things, how well actually we understand them. The other things to do the neutron background is using so-called cluster shape discrimination. The neutron cluster in the CC model and the gamma, so-called EM cluster and hadron cluster, actually they look differently, in general. And occasionally, maybe they may be similar. So we try to use so-called the shape of those raw distributions to feed into so-called the deep learning neural net. Okay, many layers, and try to see how well we actually can beat against this neutron background. So this we call CSD. Okay, cluster shape discrimination, and this actually works not bad. And we can actually compare with the training test, and even we can compare with the previous algorithm since we didn't use in the 2015. And we know how much improvement we can get. You can also compare data Monte Carlo, say, with the K-long decay, the 350 samples, and just compare the so-called neural net output. They should be, if we actually understand well, they should be similar. So basically, we can determine this is a reduction about 10 to the minus 5. It's pretty good reduction. And we also use so-called pulse shape discrimination because each, the CC model crystals channel, we actually record so-called the waveform. We call it ADC waveform. And this waveform actually we can use the amplitude and also Fourier transform in the frequency space and see the difference. It's not very big difference, but there's some improvement. It looks like about factor 10. We can add in, okay? So the combined is about 10 to the minus 6. So this is neutron background. And this neutron background, of course, give us the distribution. Like the physics that we knew, we have blob here, and also we have something in the front, because there's interactions which will show up right over here. You can see there's small gaps, but in the analysis we need to decide, okay, if anything, all those events can go in to this region, this black box region. So in 2015, we chose that time, based on the analysis that time, we chose this kind of box. So this time, and after a very long discussion, debate internally, and we try to be more conservative, we actually shift this one down. You can see. Okay. So there are other improvements. For example, we do this so-called the CV eta. Eta is about 548 MeV, also decay to gammas. But since it originated from here, and then we reconstruct as pi zero, we shift. Okay. So basically, there are quite a bit the so-called rejections on those fragments. And the last one, of course, we usually call accidental background. Okay. So when you have an in-time hit overlap with some in-time hit, say this one, okay? If you overlap with some accidental hit, it can be before, can be after, can be right over there, and then we'll basically mask out our in-time signal. So that's very problematic, and also it shifts so-called the peak, either before or after. So we try to treat this one in more carefully and without losing the so-called efficiencies. And you can see this is one of the examples, okay? And so what we do actually, we try to find out, okay, the pulse is like a single or double pulse, and try to make some discrimination based on the Fourier analysis. Then make some kind of the so-called the two pulse distance cut, okay, in terms of the number of clocks. Each clock is like 8 nanosecond, okay. So this the one we actually spent quite a bit of time and did this study. So at the end, and we fixed our the so-called the cuts. So this is the history you can see. This is 2013 data. Unfortunately, at that time, we did not have very good, the so-called the analysis cuts. Those things. We actually had one event at that time, and that time we believe it's a background event. And then 2015, it comes in like this. You can see, and there are 3 background events over here. Some of the backgrounds come from so-called the pi plus, pi minus, pi 0. And it's at bottom here, low PT. And this time, we have about 1.57 times more statistics. Where we estimate, you can see these are the estimation of the background. In 2015, it's about 0.4 event, okay, in the box. And here it's about 1.4. And you can see also, here, it's consistent. But with all these improvements, now we think we'll get down to 0.05 events in the box, and so-called the new box. And even in this black region, it's about 0.33 events. Outside, it's also quite small in estimation, and also no events seen anywhere here. This event already cut it out. So this is the status, at the end of the August. So we calculate the single event sensitivity. It's about 6.9 times 10⁻³ and this is so-called preliminary, the background estimation. Some of them actually it's only upper limit because statistics, still not big enough when we generate a lot of it. So we open the box, after a long discussion, like 2 days, in August 31st. And we open the box. So you can see how we actually get the 0.05 here based on the known background. We estimated. Then it's a shock. We open the box. Nowhere, no events basically nearby except those. Those actually we understand. Okay? There are 4 events in the box in the signal region. It was a silence actually after opening. Everybody would think about what happened. Okay, what happened? How come there's 4 events here in the signal region? So this is still preliminary, and if you want to say, okay, there's even 1 event over here. Okay, total 5 events in this blind region. So since it's a blind analysis, we think we actually did very good, estimation already. So we have to, in some sense, announce this result. However, after announcement, of course, you can do further check. Of those 4 events, one of the events is quite clear. Okay, if you remember, we have this color, counters right in front of the so-called the entrance of the veto, the decay region, the veto, so-called the front veto. So these are also the CT multi crystals, and there are hits actually here. The in-time hits is the small one, okay? The other time, so-called accidental hits, is the big one. It's not just one channel, several channels. And our cut is actually from this peak to this peak. It's a 15 nanosecond cut. This one's 70 nanosecond outside our cut. Okay. You can say, why do we decide 15 nanosecond? Okay. We decided based on the study earlier, but clearly, there are something and makes this event look like a background event. So this is one event, okay? And the other events, some looks clean, some looks may have some, accidental hit, but not in time, I think. So we're currently still, studying. So we don't quote anything right now, the so-called branch ratio, because we want to make sure the analysis, is quite, it's quite firm. I'll skip this one. This is another result we gave is k down to pi 0 gamma, which is also another limit. Okay, this one actually violates many things. So skip over. So the NA62, the charge K-ion experiment at CERN, basically they want to measure this K plus to pi plus nu bar. So K plus is charged particle, they can see it with their tracking in the beam. Also pi plus, they have a tracking device. So in general, it's a decaying flight, okay? Decaying flight experiment. Of course, the branch ratio is tiny, right? 10 to the minus 10 level. So this is the, you can see the, this is Geneva Airport. This is LHC ring. This is SPS ring, and the NA64 is north area over here, okay? Then the experiment setup, you can see there's target, 400 GeV proton beam comes in, and they have some beamline transport device in here, and for tagging, like a count tagging, and there's a vacuum, just like Kodo, with many vetoes, except they don't have hermetic veto. They have so-called planned vetoes, and then decay. The charge can decays here with this so-called the wire chamber we call straw chambers, and there's a re-imaging Cherenkov counters for party identification. There are muon counters, all these things, try to help them to reduce the so-called the backgrounds. So basically, the momentum is about 75 GeV of the K-ion beam, and it's 1% the resolution. And the divergence is not big, 100 microradian. Transverse size about 60 times 30 millimeters square. And the composition you can see is not pure K. That's why they need, good tagging. K plus about 6%, pi plus about 70%, proton about 24%. Okay. All right. So basically, you can see the way they ran, some test run in 2014-15, and the first physics round, 2016, they have one event, 45 days, and this year they analyzed 2017. I think this data, it's about 160 days. They still have more, they can analyze. So basically, this corresponds to about 2 times 10 to the 12 K plus decays. To analyze so-called to search for this K plus to pi plus nu bar decay in flight, they use this so-called missing mass square parameter. Compare the measured K plus momentum and the pi plus momentum in the 4 moment square. You can use that square, and it's 4 moment square. Okay, so then of course you have a major decay mode from K plus to pi plus pi 0. You have those leptonic decays, you have the 3 pi, those decays. You can see the branch ratio. And that means this peak is from this, okay? So typically you cut away this peak. Then there's region 1, region 2, there are other contribution from those decays, in those lines. So you can see this, the log scale. And basically they chose the pi plus momentum between 15 to 35 GeV, and with the particle IDs and the vetoes. So you can see this is typically the Monte Carlo distribution like this. All right. So one of the things, of course, they want to figure out the so-called pi zero rejections, and this is the pi zero rejection versus the pi plus momentum. You can see the rejection factors from 10⁻⁷ down to 10⁻⁹, and this is their so-called the optimized signal region. And based on this, also they can, set a so-called a limit on the pi zero decays to invisible. Okay, 4 times 10⁻⁹. So now back to k pi nu nu bar. Okay, k2 pi nu nu bar. So here you can see between 15 to 35 GeV, you have these two the regions as a search region. They also did the so-called blind analysis. So right now these two are not open, but they have some control region here. They can also look for those outside region. So basically these are the so-called background study, and see how much they can predict the background inside. So the source of the single event sensitivity, you can see based on their measurement. Basically, you can just use this region, okay, and you can get down to about 0.39 times 10⁻⁻⁻, and that means if you use the previous measurement, you can expect about 2 events, so-called pi nu nu bar event. And these are their uncertainties about their, trigger acceptance, those things at 10⁻⁻⁻ level. So the k plus to pi plus pi zero background, and this background, of course, it's a peak with some kind of tail with some, some loose cut, that's right. So they can study the shape. They can actually using the tails to predict the so-called the background in those regions, and then they expect the background just from the k plus decay. Okay, they already expect 2 events, but all the others, if you add it up, it's about 0.6 event just from k plus. So this looks small. Okay, however, they actually have a background which they did not anticipate before. When the charge K-ion comes in, and they have this so-called achromatic, magnet to bend this way, then send back in here. And sometimes, something, it says, okay, can, for example, can come out here, maybe decay, and then make 2 gammas, then the pi plus go this way. So you can have some fake, so-called the fake decay vertex, which is not actually along this beam line, this straight beam line. So that's become a problematic, because they have a tech counter here, finite size, and that causes some distribution over here. They actually have to remove it. You can see it. They have to remove it in this XY plot in the column here. Okay. So this is unexpected. They did a study and tried to estimate how big, almost 1 event level. So if you add it up, okay, it's 1.5. Now, even they expect 2, and then have 1.5 background event, and that means the signal background is not great yet. So they open the box. They also look at this region first, and they estimate about 0.62 background, and they got 1 event over here. And then they open the others. You got 2 more events in here. Okay, and there's no event, of course, in this region. So basically, 2017 result, the new result. They observed 2 events, single event sensitivity, and also background. They can convert to the so-called the upper limit for the measurement, And say if you look at 90% confidence level, usually it's about the observed less than 1.76 times 10^-10. Okay. So this is the based on the two events, and also they can study the so-called the missing mass square of different contributions. Seems okay. So if you add up 2016-17 results, 3 events total, expect background is 1.65. So it doesn't change much about the conclusion yet. So this is the comparison. You can see this start from 1970s. First time when the experiment tried to do this k plus pi plus mu bar, it set an upper limit, and gradually coming down to 10^-9. Finally, actually, Brookhaven saw the 7 events, set the branch ratio here, and of course, theoretical prediction evolved this way. Okay, so over here. So this result seems to be larger than the theoretical prediction. However, N62 right now seems to be low. Okay, so maybe just as a fluctuation, the natures usually try to fool us. So basically, this is the summary of their result, and they can set the k plus pi plus mu bar. Say the central value is about this size with large error bar, or the limit. And the COTO, of course, in 2015, we already set the upper limit 3 times 10^-9. And currently, our single event sensitivity is below so-called the gross linear bound, plus 7 times 10^-10. And we saw 4 events. Maybe 1 is background. The others will still investigate. And that, in some sense, still right now consistent with this upper limit. Okay. So this is the based on the current, so-called the NA62 and the COTO's upper limit. This is still the region right now, unexplored, and I think we need to taking more data, both experiments, and try to refine. And maybe one day we'll reach this region. We don't know, how big it will be, this standard model. All right, so JParc, what's next? JParc right now, we finished running in 2019 with a 50 kilowatt, beam power, and we'll run next year, and probably around this. And then we'll be shut down to increase so-called the accelerator beam power. Hopefully we can reach about 100, in 2022 to 24. And this is the current plan. And if based on that, maybe you can come down this way. You can see the sensitivity reach the so-called single event sensitivity reach to so-called standard model level. All right. So I think that's it. Probably stay tuned, because we don't have a final result yet.
Okay, the floor is open for questions and comments.
What kind of improvement you can imagine in the detection part?
Improvement in detection?
Detection, yeah.
Yeah.
Use the scintillator, the vehicle,
No,
whatever.
the detection, the whole experiment, at least for COTO, is in some sense is the so-called the Vito inefficiency. Okay, because inefficiency already reached 10^-4, 10^-5. So detector efficiency is 0.999 something. Okay, so the question is the background.
Right.
Then the question, how can we improve that? Yeah. So the background improvement, one thing, almost every year, we run about 2 months. But actually we have improvement upgrade in various fronts. including, for example, DAQ, including we're adding the so-called the second plan of charge veto. So we have 2 charge vetoes. So we can improve this so-called inefficiency. And also we actually also add in so-called the inner main barrel vetoes. That was a very hard task actually to do that because it was not designed initially. So for CCMODEC, maybe we do have one improvement in 2019. CCMODEC usually read out from back with the photon modified tubes, PMTs. But in the front, this time we decide to add in so-called the MPPC chips for every channel. So this actually can give us timing. And there's so-called the neutron event, hadron event, and the photon event. They actually, the timing looks different, okay, from our test. So we add in this, and we took some data. We're still analyzing, and also want to see how good is the performance. And we will also use this in the next run. So that means in 2016 to 18, we did not actually use this as a way to differentiate. So I think we have more handles right now. At least we can check our background. Okay, those background.
About the neutron activation, all those things.
Yeah, the neutron is from the beam.
Right.
Yeah, how clean is the beam actually is not easy to actually right now to change it because we share the beam. Okay, if we are the only experiment, then we know how to design our beam. But when we share the beam, share the target, then basically the so-called halos is bigger than we expect before. It's almost 10 times bigger. And that one's very hard to actually knock it down. We probably still will try to do something, but I don't know how successful. Yeah.
Other questions? I think you must have estimated the expected number of events in your signal region, right? For the Kodo experiment.
Oh, signal region? Wait a minute.
Yeah. So
Let's see.
the number. Those are the
Okay,
numbers.
this is loose in the cut. Actually, there's three background events showed up in here. But anyway, let me go back. Where? How do I do it?
So I just want to know what is the probability that the observed 4 or 5 events are just statistical fluctuation?
Okay, it's a good question. Okay, we did calculation. 6.9 10^-10 compared with 3 times 10^-11. It's only about 20 times, right? So there is a 5 to 6% probability one event can fluctuate up. Okay, so that's one. But 4 events definitely is above the gross linear bound right now. Okay, but still consistent with our previous upper limit. And so if one event we think is background right now, so then 3 remains. We don't know that 3 right now. We should treat it as a signal or background yet. We need probably another round analysis right now. We think it's maybe 2 to 3 months. It's not an easy process. Yeah.
Okay,
We
so
spent
that
already
means,
2 years on this one.
so that means after Chinese New Year, you should have the.
Hopefully. The target actually, I think by January, we should have something. Yeah, more firm.
Okay.
There are a lot of the things takes time to generate those Monte Carlo, and it's very high sensitivity Monte Carlo with the so-called overlays, and there are different kind. At least so-called the type of backgrounds, and we already studied quite a bit. But right now, we're still thinking. Okay, we have some list, checking many things, and there's a few right now we're still checking. See, we thought it should be very small, and some we verified, some we're still checking how small. And the other thing is that the so-called the accidental. I mean, that clearly, okay, we may have to do something to maybe redo the analysis to optimize that.
Okay. Other questions? Well, if not, let's thank Professor Shaw again.